All right. Welcome back. Today we're looking at lowest common ancestor of a binary search tree. This is going to be an easy question. We're still on easies, still on week 1. Doesn't sound easy. It sounds closer to a medium. Oh, looky here. Did not do that on purpose, but you click into it and it actually is a medium. So, Grind 75 is going to update that. Let me close these bookmarks real quick. All right. So, given a binary search tree, find the lowest common ancestor LCA node of 2 given nodes in the BST. According to the definition of LCA on Wikipedia, the lowest common ancestor is defined between 2 nodes P and Q and the lowest node in T that has both P and Q as descendants, where we allow a node to be a descendant of itself. Okay, so I'm going to take some notes here, but a LCA is the lowest node where P and Q are descendants. Okay. Just writing my notes here. Let me just move this to the side and then you can see it at the same time. All right, let's look at the first example. We got the 6, we got the 2 and the 8, and the P is 2 and the Q is 8. So because 6 has a dot left, that's 8, and a dot right, sorry, dot left, that's a 2, and a dot right, that's an 8. The 6 is the first one to encounter the fact that the 2 and the 8 have been found. Okay, it's interesting. So example 2, there's a 6, 2 and 8, so it's the same tree actually. And the P is 2 and the Q is 4. So the 6, if we're probably going to solve this recursively because it's a tree, it's a natural way to solve it. You're going to call the recursion function on the 2 when we recur on the 0. So the 0 is not going to give you any type of found. But then the 2 goes to the 4, 4 goes to the 5, 5 goes to the 3. The 3 won't return anything. 5 won't return anything. The 4 will return something of value. Okay. And then let's think about it. 6, 2, 0, 4, 3, 5, and 8 here. 7 and a 9. So when we call this function on this node, because we're doing it recursively, we'll probably call it, and it's going to, be called on every node that is a child, right? And the first to evaluate is going to be, probably something that's lower in this chain, one of these leaves, right? First to evaluate will probably be, if we're going left and then we're going right, will probably be this 5. This will be the first one to evaluate. All right, so let's put this 5 in here. This is the first one that's going to evaluate. And the way that I would think about it is, what is the return value that I want from this 5 going upwards? In fact, what is the return value of our recursive function in general? So let's say a function takes a node and it's going to return some type of values, right? So when we think about the skeleton of these types of problems, then we're probably going to want to call this function on the node dot left. We probably want to call the function on node dot right. And I'm going to put recur to represent recursion here. And, typically you maybe want some results from this node dot left. I'm just going to say from left here, and then from right here equals this recursion, and then you want to do some type of logic, right? So some logic, I'm just going to write check here. Some logic is going to take from left, it's going to take from right, and then it's going to do something based on it, right? So if yes, return this, else return something else, right? That's typically what the scaffolding for a tree recursive problem looks like, because you want to, you know, as we said here, you want to call this on the root node, and then it calls it all the way down, left and right, all the way down, right? Let's just make this clear by putting in these lines. So what is the thing that we want to return, let's say from this bottom node? Well, we at least want to return, you know, have we found P? Have we found P? Right? Is P a descendant here? We want to return, have we found Q? Right? It's P and Q. These are the two targets that we have. So we want to know, have we found Q? Right? And then that's at least what we returned. And then maybe, have we found the lowest common ancestor already, right? So if you were writing this function and you had this logic here, what type of logic would you want, right? What's inside of this check, right? What's inside of this check? Inside of the check is something like, well, if, you know, from left and or from right already has the lowest common ancestor. So if let's say we're calling this on this 2, right? If 2 is the lowest common ancestor, what the 6 should realize is that we're passing the lowest common ancestor upwards, right? So if something already has the lowest common ancestor, we want to basically just return it, right? So if it has the lowest common ancestor, we're going to return the LCA. Else, we're going to want to do some other logic, right? Well, else, if these the lowest common ancestor has not been found, then maybe one of P or Q has been found. And maybe the current node is that P or Q, right? So, so let's think through how we do that. So, you know, else, I guess if P was found, you know, oh, you know what? So the current node can also be P or Q, right? So it seems like the values that we want to return from here is at least lowest common ancestor, if P is found, and if Q is found. And this is kind of like a tuple that gets returned. This is good. This is good. Okay. So I think this makes sense, and it makes sense. I think it'll start making sense when we code it as well. So we have the lowest common ancestor, and let's think through how to just do a regular traversal, right? So we're going to create a go function here that takes some type of node, and let's just say it just prints the node. It can call go.left, it can call go.right, and if the node is none, then it just does nothing, just returns. And we're going to initially call this with the root, right? So if I run this, you would see these printed in order of this traversal. right? So here's your standard out. So this is the exact example from, is this the example from the problem? 7, 9, no, 3, 5. Okay, so this is the example from it. This is the example 1, right? And our standard out is going from 0, which is the leftmost, and then 3, and then 5, and then 4, and then 2, right? And then it should be 7, right? 7, 9, 8, 6, right? So these are all the, I should probably just have printed no.value. Let's print no.value, no.val. Perfect. So this is the ordering in which I drew this, right? In fact, let me just write in red. This returns, right, upwards. This returns upwards, this returns upwards, this returns upwards. And then this, and then finally, sorry, there's some order here, right? So what do we want to return upwards? Well, it's these two situations, right? So let's say from left equals this, and from right equals this. And I guess we want these 3 pieces of information. So I guess we should actually say LCA or P found or Q found. And let's just make sure this is the left version. This is the right version. Sorry, these are all the left version. Okay, I'm just going to say left, make it super clear. Okay, so you know, if the left LCA exists, we actually just want to return left LCA, and we want to return this tuple. So this would be true, and this would be true. If the right LCA exists, we just want to go ahead and return the right LCA, and this would be true, and this would be true. Right, so if 2, let's just imagine, you know, we're calling 2 right here. 2 is the LCA, and nose is the LCA. Then we want to return, you know, this tuple up to the 6. And 6 is going to have left LCA, and we want to go ahead and return that. So actually from here, we want LCA found is going to be this, and we're not going to use these two, but LCA found is going to be this, and then we're going to return LCA found from here, right? So this is the return value of this go function. Okay, so if it's not found, so LCA found, LCA not found. Okay, so we want to think through, we have our check. Our check was this logic, LCA being found. It looks like I didn't finish it. But what else? What else is this logic? Yeah, I definitely did not finish it. So what else needs to be checked? Well, the current value needs to be checked, right? So no.val could be P or Q. So got to consider that. And so if if it's not P and it's not Q, then we want to return something like LCA is false and node.value equals P, or node.value equals Q, right? If there's a P, then we want to do, you know, the corresponding one. If there's a Q, we want to do the corresponding one, right? And that would be the code. Makes sense, right? So let's make this, let's just shrink this right here and verify that we have the structure, right? So we have LCA found. I'm going to make this, so that's the red part, and this is the green part, right? So this would be in the diagram, the red area. Probably should have switched the colors. I'll make this red and make this green. Right, so the red area is we found the LCA, we're going to return upwards. And else we have not found the LCA, so we want to do some logic, right? So if the left P, so let's just say P found equals left P found or right P found. And then Q found equals left Q found or right Q found. So if P found and Q found, then we actually know that this current thing is the LCA, right? So I forgot to put the case here, but you know, if both found, node is LCA. So this is the first case. This is the one we're working on now. Just gonna make this gold. So this is the one we're working on now. If they're both found, then we know that the current one is the LCA. So let's think about this node in example 1, 6. If 2 returns true for one of them found, if 8 returns true for one of them found, whether it's Q or P, then we know that this 6 is the node, right? So the LCA is actually this node right here. So it's node here, this is true, and this is true, right? So if and I guess I can smash this into one else statement, or else we're going to return interesting. I guess there's another case I haven't thought about where what happens if the current node, so in this example 2, is one of the descendants that we're looking for. So that means, let's say from the right side, it would have had Q as found. So if only one of them is found, then we have to special case it, right? So here, if they're both found, then this is going to be the first one. Here, if P is found, so only P is found in this case, then we want to return if the node.val equals Q, then we know that this is going to be the case, right? This is this right here. True, true. Else, we want to return, you know, none here. And the fact that P is found, I should probably just switch these. So This is P found. This is P found. Go ahead and put it up here because P found should actually be true here. Q found should be true here. If they're both found, then this is going to be a new LCA. If only one of them are found, if it matches the other one that we're missing, then it's going to go ahead and be, I can say something like value matches Q, and that's going to be no.val double equals Q. Right? And the idea is that here this would be true, and here this would be false. Right? I feel like that's actually more clear. Okay, so if only one of them, then it's Q. If it's only Q found, then if no.val equals P, then same thing, right? Where this is going to be true, and Q found is going to be here, and we know that's going to be true. Or else, we're going to return none here. This will be false, and Q found will stay the same, unchanged. And then if they're both untrue, so if not P found, and I mean, it's only the last case, so I can just return here. So I can return that none of them are found, but I can go ahead and say no.val double equals P, or no.val double equals Q. So let's walk through this code. You have a diagram like this, right? And we saw the ordering that we saw before, but let's just imagine we are returning from one of these, right? So the function, when we're calling it on the 0, is going to return none, and because they don't match, it's going to return false and false, right? And then the function is going to be called on the 3, and it's the same thing. It's going to be none, false, false. The function is going to be called on this 5. It's going to be the same, none, false, false. Well, let's talk about what we're looking for. Let's look at example 2. Right, we're looking for a 2 and a 4, right? And then the function is going to be called on the 4, and one of them is actually going to match, right? They're both going to be, oh shit. Okay, you couldn't see that. The function is called on the 0, the 3, the 5, the 4. The 4 actually matches, right? The first one's still going to be none, but which one does the 4 match? Does it match P? No, so this is going to be false. Does it match Q? Q is 4. So yeah, this is going to be true. Perfect. So what's going to happen when we return the function on the 2? So the 2, it's going to reach, so Q was found, right? LCA wasn't found yet. Q was found, so it's 36 right here. The 2 matches, actually. It matches P. So what's going to be returned is this node 2 as the LCA. And then it's going to return true here because P was found. And it's going to return Q found. We know Q is going to be found because Q was found on one of these left rights, right? It was found on the right. So when 4 returned, right? This one right here, when 4 returned as, go at no.right, right? So what's being returned from here is this, right? This is a return value of this, right? So Q was found was true. So this one would be this. And then, you know, we're going to continue to call this on the 7, which is going to be none. FF, we're going to continue to call this on the 9, same thing. On the 8, same thing. And then importantly, we're going to call this on the 6. So what's the 6 going to look at? Well, the 6 is just going to look at this first one, right? It's going to look at what's being returned from here is whatever's in this green box. Right. So it's in this green box. We're going to look at line 13, left LCA, left P found, left Q found. This is going to be the exact node. This is going to be true. This is also going to be true. Not that it matters. We're going to get to line 20, and we're just going to return straight out that this is the left LCA. Right. Totally makes sense. So what's going to be returned here on line 44 is that this will be the left LCA, right? So if we run this, we hope to see that non-iterable object. Okay, I see. So when node, so yeah, so instead of returning anything, I just kind of return none here. I should return false, false, right? And then at least it keeps it a tuple that can be destructured. Okay, so the output is null. That's fine. Let's just see if the code works. And if the code works as we expect it, that's a win, right? And then we'll fix whatever edge case is happening here. Okay, so where is the print happening? The print is happening here, and I'll say not found. So it's happening here because this is the value of the node that we're currently iterating on. So it's 0. And I'm trying to think of the best way to log it to be informative. So I think this these would be informative. So whether or not P was found. I guess if there was an LCA found, that would be pretty informative. So returning left and right. And then is there a return for every single case? There is a return for every single case. The LCA is here. Okay, so let's just log these and see if that makes sense. Okay, so the P found was false. Perfect. The Q found was false because when you're at the 0, there's nothing at the left, there's nothing at the right. It's exactly what we expect. For the 3, P found is false. Q found is false. Exactly what we expect. The 5 also, because they're leaves. Now the 4, yep, nothing from the 3 or the 5. Should set that off. From the 2, we actually expect at this point well, what's Q here? This is 2 and 8. Okay, so we expect that to be false. 7, false. 9, false. The 8, false. The 6. Okay, so at the 6, we actually expect these to be true, right? Because on the 2, we should be at this point where Q, so you know that value, one of these should have been true, right? Like it should have been node is P equals node.val double equals P, node is Q, node.val Q, right? And if you print these, this should have for sure node.val, P is P, and then right, so here is where the 2 should have returned true, right? So let's go to where the 2 is. That's weird. Oh, yeah, that's perfectly fine. Oh, I see. P and Q are not. I see. So P and Q are actually nodes. So I did not know that. Well, I don't need them to be nodes. I'm just going to switch them. P equals P.val and Q equals Q.val. I don't know that having the reference is useful for the rest of this problem. So I'm just going to not deal with that. Okay, so that solved it. So Q and P were tree nodes. They weren't single values. And I could see test cases where that actually breaks, but I don't think that's a problem for us. Okay, so I guess we didn't need to print all those things. I guess it was just a type error. We didn't really have any logic issues, but like at this point, we can think about how to refactor this to make it less error prone. So yeah, let's just think through how to make this less error prone. So if P is found, then what's this? A P and Q are not equal, so I could have taken advantage of that. Right, because if I knew they weren't equal, I could actually just return. No, it's fine. I mean, this code totally makes sense. All right, so that's it. This kind of just matches the diagram that we had here. What we did was we thought about what information we wanted to return, right? So here, have we found P? That's important. Have we found Q? Also important. Have we found the lowest common ancestor? Also important, right? Once we know what we kind of want, we know that the skeleton, the scaffolding of many of these problems is similar, right? We're going to have some Go function that takes a node, and then it's going to return some set of values. We're not sure yet. And maybe it's these 3 values, right? It could be something else based on the problem. We're going to call recur on left. We're going to call recur on right. Sometimes you don't see it like this, right? Sometimes you'll see it as the return 1 plus recur on left plus, recur on right if you're doing something like height or depth. Sometimes you'll see it as like, return max of these things. But here I'm doing it explicitly, right? Like here, line 15, line 16, I'm just explicitly saying, let's call it recursively on the left. Let's call it recursively on the right. After that, we have some logic. We have some logic that helps us check based on this information that we just got, right? And that's helpful because if we didn't do that, why even call recur, right? So this left, this right, it's going to have some logic check. And for us, the logic check was, have we already found the lowest common ancestor? Because if we already did, let's just return it straight up. Okay. So here, this is our green. This is our happy path. Best case, we already found it. Let's just move on. Otherwise, we have to do some logic, and this is kind of messy. But if both are found, right, then this current node is the lowest common ancestor, right? Right here. If both are found, then the current node is the lowest common ancestor. Otherwise, the node.val could be the one that's P, could be the one that's Q, right? So let's actually get rid of this logic. Doesn't actually make sense here. It's actually in here, right? Delete this. Delete this. Just return something else. Return something else. Okay, so if it's not P and it's not Q, right? Which is what we had down here. If it's not P or it's not Q, then we're going to do something. Otherwise, I'm going to move this to the bottom then. Okay, so there's 2 cases here. Let's just handle that. If it is P, right, if P was already found, node.value could be the Q, could be the missing Q. If it's the missing Q, set that to true. Otherwise, set that to false, right? And if we set that to true, that means we both found P and we found Q. This node is going to be the lowest common ancestor, right? And Q is just the same thing. Q is the same thing, but for looking for P. If Q is already found, it's a solved problem. Great. We're going to deal with P now. If we find P, then this node is the lowest common ancestor. Otherwise, we do this, right? And to make it more explicit, because in my diagram, I didn't have it like that. My diagram, it's over here, is not P and Q. Then to make that more explicit, if, not P found and not Q found, then we do this one, right? Hopefully this still runs. Confident it does. We didn't change any logic here. So let's submit this, see how it goes. There's probably some cases that, ooh, okay. So that's great. Solve the problem. Awesome. Awesome, awesome, awesome. I don't see any obvious code changes I want to make, but I am pretty sure this follows the plan that we laid out, and that's what's important. We adjusted to some changes, but the plan that we laid out with the scaffolding that we will use to handle almost every binary search tree or binary tree is going to be this exact scaffolding, right? And the way to think about it is the way we thought about here. What is the return value that we want? And then we can kind of map out what it would be like if we called the function on each one of these nodes, right? And this is what this is really useful for, right? let's look at what each function is, the return value of it. And when I'm writing it there, you mentally want to think about, well, what would it look like if these were mapped to their return values, right? So let me be a little bit more clear about that. Let me just get rid of all the fluff here. Okay, so this, right? Well, this is here. I don't know if there's enough room. This is here, right? That's what's being returned from it. What is this? This is here. That's what's being returned from it. What is this? This is here. Right? That's what's being returned from it. This exact thing is being returned from here. So this 2, right? This exact thing is being returned from here, right? And that's a tuple. This is being returned from there. That none. This will also be none. This will also be none. Right? Let's delete that. So this is what the code for each node looks like, right? That returns here. Go ahead and delete this. Move this down. And you're seeing that the return values spatially look like this, right? So when the 6 has to make a decision, the 6 is making the same decision that all our other code makes, which is from left, what's going on, from right, what's going on. And then can I call a check based on both of these, right? And the check that we had is basically going to look at the first value as the LCA. There's no value here on the side, but imagine there is. And if it is the LCA, just return, right? Return this tuple, basically. All right, thanks a lot. It's been really fun. And I'll see you next time.